Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on surds. So what exactly are surds? Well, surds are a type of irrational number. So remember, irrational numbers are just not rational. Rational means the number can be written as a fraction or equivalently as a terminating or recurring decimal. So a number like -2/3, that's rational because it's a fraction with integers. Any fraction with integers is rational, even if it's something weird like 113/330. Okay, they're rational. Terminating decimals like 0.25 are rational. This is terminating because the numbers after the decimal point stop. Something with a recurring decimal is also rational, like 0.3 recurring, because that actually is the same as a third. It can be written as a fraction, and 0.25 is the same as a quarter. So all of these are rational numbers. Whole numbers are rational too, like 4 or -7. They're all rational numbers. So irrational means it can't be written like this. It can't be written as a fraction with integers. It can't be written as a terminating or recurring decimal. So one irrational number you probably know about is pi. So you can't write pi as a whole number divided by another whole number. If you were to look at the decimal expansion of pi, all the numbers after the decimal, they go on forever, but there's no pattern to them. So the decimals are not terminating because they go on forever, but they're also not recurring because there's no pattern to them. So it turns out you get an irrational number every time you square root a number that's not a perfect square. Now, if you've forgotten what perfect squares are, they're just the square numbers, 1 squared, 2 squared, 3 squared, 4 squared, and so on. These are all perfect squares. So if you square root a number not on this list, you get an irrational number. So for example, the square root of 2, that's an irrational number. If you put it on your calculator, you get like 1.41, blah, 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 goes on forever, and there's no pattern to it. So it's not exactly equal to 1.4, which would be a rational number, but we can't write it as a decimal that stops. Sometimes we need to be really precise in our calculations, and we want to write the square root of 2 exactly as it is. We don't want to round it to 1.4 or 1.41. So it's easiest to leave it like this. Root 2 is the exact number that you square to get 2. It hasn't been rounded or anything, so we can use it if we need to be precise in calculations. So another number that doesn't appear on the list below is, say, 30. 30 is not a perfect square, so that means the square root of 30 would be irrational. Again, the square root of 63 would be irrational because 63 is not a perfect square. The square root of 64, however, would be rational because the square root of 64 is just 8. 64 is a perfect square. So it's only when you square root a non-perfect square that you get an irrational number. And as I said, we want to leave it as the square root of something because that's an exact answer rather than needing to round it, which will make our calculations imprecise. So now we're going to go through operations involving surds. We'll start with multiplication and division. It turns out that these operations with surds are very easy because the rules are very intuitive. They're what you'd expect them to be. The reason is because square rooting undoes raising to a power, which is repeated multiplication. So surds are compatible with multiplication and division. So this first rule here says if you're multiplying two surds together, it doesn't matter whether you square root them first and then multiply, or you multiply them first and then square root. And a similar rule for division. If you're dividing surds, it doesn't matter whether you square root each of them first or you divide them first, then square root. So let's make this clear with a couple of really simple examples. So for example, if I have the square root of 14 times by the square root of 11, that would just be the square root of 14 times 11, which is 154. So if you put this in your calculator, you'd get the same as if you put that in a calculator. Both are irrational numbers. So let's say I had something like the square root of 27 divided by the square root of 3. So the second rule tells us what I can do is just divide the two numbers, 27 over 3, and take the square root. But of course, 27 over 3 is 9. The square root of 9 is not a surd, actually. It is a rational number because 9 is a perfect square. The square root of 9 is 3, so we write it like 3 because that's more simple. So we've just shown, very interestingly, you can take an irrational number. Root 27 is irrational because 27 is not a perfect square. We've got an irrational divided by another irrational, but we ended up with a rational. So the only way this is possible is if this is 3 times this. It turns out that this implies that the square root of 27 is 3 times the square root of 3. So how do we get that? Well, going from something like this to something like this is called simplifying. Simplifying surds is sort of like simplifying fractions. What we want to do is we don't want to change the value of the number, but we just want to write it in a way that's simpler to understand. So just like when you're simplifying fractions, you know that 10 over 20 is the same as a half. They both have the same value. We haven't changed the value. It's just half is easier to work with than 10 over 20 because it has lower numbers, and it's the same with surds. When we simplify a surd, we want to not change the value of the number, but just write it so the number inside the square root is as small as possible. So in order to simplify a surd, what we need to do is find the largest square factor, the largest number that goes into the original number in the surd that is a square number. So for 27, we look at which square numbers go into 27. Well, 1, yeah, okay, but 1's not helpful. The next square number is 4. 4 doesn't go into 27, but 9 does. So what we do is we take our square root of 27 and we write it as the square root of 9 times the square root of 3. The reason I chose to write it like this is because we want this first one to be a perfect square. That's why we need the largest square factor. Because if it's a perfect square, then when we square root it, we'll just get a whole number. So that's why square root of 27 is equal to 3 times the square root of 3. Because the square root of 9 is the same as 3. That's how we simplify them. Let's look at another one. So let's say I want to simplify the square root of 242. So I want to not change its value, but I want to write it as a surd that has a smaller number inside the square root. So I need to find the highest square number that goes into 242. So what I'll do is I'll start with square numbers that are close to 242. Well, obviously, I can't, use 225, which is 15 squared, or 196, which is 14 squared. The highest is actually 121, half of 242. So I write this as the square root of 121, because that's the highest square number that goes into 242, times by, so what do I times by 121 to get 242? Of course, 2. Okay, so you can see that I'm sort of using the opposite of this rule up here. So the square root of 121 is 11. So this is just the same as 11 root 2. This is considered simpler because the number inside the square root is smaller. So just as when you're trying to simplify fractions, when you're trying to simplify surds, not all surds can be simplified, just like not all fractions can be simplified. So up here we had an example of 2 that cannot be simplified. Why can square root of 14 and square root of 11 not be simplified? Because there are no square numbers other than 1 that go into them. So 14, its only factors are 1, 14, 2, and 7. So 14, 2, and 7 are not square numbers, and as I said, the square root of 1 doesn't help us. So we can't simplify this any further. Similarly with 11, its only factors are 1 and 11. 11's not a perfect square, 1 is not helpful. So not all surds can be simplified. They can only be simplified if they have a square factor other than 1. All right, let's now look at addition and subtraction of surds. So when we're adding and subtracting surds, it's a little more complicated than multiplying and dividing because addition and subtraction aren't necessarily compatible with powers. So what is actually happening is we can only add or subtract like surds. So it's similar to algebra where you can only add or subtract like terms. If you have something like 4x plus y plus 2x in algebra, you have to take the like terms and add them together. and leave the unlike terms alone. And so it is with surds. Let's simplify this expression in blue. Because there are lots of subtractions and additions, we have to find the like surds. So like surds are just ones that have the same number in the square root. So square root of 13 and positive 5, square root of 13, like surds. So root 13 plus 5 root 13 is 6 root 13. And then this one here and this one here are like surds because they both have a root 7. So minus 2 root 7 minus 4 root 7 is minus 6 root 7. So just like when we were adding and subtracting terms in algebra, if we had to add terms, we just added the coefficients. We got 4 plus 2 equals 6. We do the same here. This is like a 1 plus 5 gives us 6. And of course, minus 2 minus 4 gives us minus 6. So let's simplify this second expression in blue. So just as we do in algebra, we can do whole numbers by themselves. We can do them separately. So it's 10 plus 6 is 16. So minus root 22 minus root 22 is minus 2 root 22. Once again, if no number is written in front, you can assume it's 1. And then the root 11 by itself has no common factors. Don't get fooled into thinking that root 11 and root 22 can be added because 11 is a factor of 22. Unfortunately, it doesn't work like that. So this is our final answer. It cannot be simplified any further because there are no like surds. So what makes adding and subtracting surds even more complicated is that we can only add or subtract like surds usually. There are times when you'll get surds that don't look like surds but actually are. So let's say I wanted to do square root of 28 plus the square root of 63. I can forgive you for thinking that given that what I just told you, you can't actually simplify it. It turns out you can. You can add these together because when you simplify each surd, they will be like surds. So let's simplify each. So square root of 28, the highest square number going to 28 is 4. So it's root 4 times root 7. And the highest square number that goes into 63 is 9. So root 63 is root 9 times root 7. But of course, root 4 is 2. Root 9 is 3. So actually, these two are like surds. And then you can add them together and just get 5 root 7. So how do you know when you're looking at surds that need to be added or subtracted whether they're like surds? Well, what you have to do first is see if either surd can be simplified, because that may make them like surds. So in our first example, it turns out that they couldn't be simplified. Square root of 13 can't be simplified, nor can square root of 7. And similarly, in our second example, root 22 and root 11 cannot be simplified because none of those numbers, 11, 22, 7, or 13, is divisible by a square number other than 1. So we actually did do these right. But this one here, it turns out they could be simplified. So whenever you're adding or subtracting surds, first see if you can simplify either surd, just like I did on the previous slide. Alright, sorry for the long video. Thank you so much for watching. This has been the luckiest maths teacher in the world. Have a great day.